All right. Hi, everyone. I'm Akshay. I'm at the Department of Data Science at NJIT. This work is on generalization bounds for neural networks with low-rank layers, joint work with Andrea Pinto, who's in the audience here, and Tomaso Poggio, both from MIT. So this is a rough outline for what I'll be talking about today. I'll try to introduce and motivate the problem, then do rank separation for one layer of a network, and then present our main result and try to give some, try to discuss it. So for deep networks are a highly expressive class of functions. You can basically, if you look at this picture from Zhang et al. In I think 2020, 2017, updated version 2021, you can basically fit data with even random labels. So this means the number of parameters doesn't really provide a good complexity measure for explaining how deep networks can generalize well. And we usually try to find an alternative low complexity or an alternative measure of complexity that which correspond to the solutions that stochastic gradient descent actually finds in order to obtain better generalization bounds. So in this work, we're going to try to characterize these low complexity solutions through the Rademacher and Gaussian complexities. And there are textbook results that can be used to bound the generalization gap using Rademacher and Gaussian complexities. So so since about 2017-ish, when the understanding generalization paper came out, people have been trying to find different notions of complexity that are using which you can get better generalization bounds for networks. And one of the most popular ones is to say that neural networks or stochastic gradient descent or gradient descent finds minimum norm solutions, and we'll try to characterize complexity through the norms of the parameters of the neural networks. And one of the I guess most important results is from 2018, Golovich et al. On Rademacher complex, where they bound the Rademacher complexity in terms of a product of the Frobenius norms of the layers of the networks times a square root depth. The proof strategy here basically peels the layers one by one, and they do it in a smart way to avoid an exponential blowup in with respect to the depth. But this is basically the strategy that's also followed by a number of different other papers which use which all try to bound the Rademacher complexity of deep neural networks. And I'm probably not going to succeed in saying that this is wrong, but I'm going to try to argue that we should maybe think about it in a slightly different way. So our way into this problem was basically I also work on trying to characterize sparse and low-dimensional structures in deep networks, studying the solutions that you actually obtain during training. And one of the inductive biases, or one of the biases that you see in when you train deep networks is this phenomenon of neural collapse, which was first identified 2020 by Vardhan Papian and Dave Donahoe and XY Han. And here, basically, there's a dramatic simplification of the weights and the representations in the last layer of a network, where all of your training samples concentrate around their class means, and these class means spread apart to be as far away from each other as possible. And there's a duality between the weights and the representations. And we were able to also track this not just at the top layer, but also in a number of the layers before that. So what this means for the weights and the features of a deep network is that they are basically low rank, and the rank corresponding to the number of classes at the top layers. And a few other things also happen. The weights and the features align with each other, so you can imagine that the weights of different layers also align with each other. But we like to use this implicit bias of this solution, that the neural club solution that you get while training deep networks. We like to see if you can use this bias to get better generalization bounds. And in this paper, we mostly track. We're going to mostly use the low rank property of the weights of deep networks to do this. So first, before I go into our main result, I need to convince you that I can't just plug this into plug in a simple bound on low rank layers into previous work and get something good. So first, let's compare low rank and full rank functions in a key step in the Golovich 2018 paper. So their key lemma here is this is how they're able to peel the Rademacher complexity from one layer to the next, and here they get a bound. Assuming a Frobenius norm bound on the weights of a layer, you can get this. You can peel off that the one layer and then get the complexity as the Frobenius norm times the complexity of the previous layer. And into this step, if you plug in a low rank assumption on the weight matrix, you cannot really show a separation. In fact, rank 1 matrices achieve the same bound as full rank matrices, and you can basically show this by just set the matrix W to be a normalized version of the outer product of this vector, basically. And so we need to do a little more work than just plugging in low rank matrices into an existing generalization bound. And what we do, not too complicated, we make two particular changes to the step above. So first, instead of considering a bound on the spectral norm, so considering a bound of the Frobenius norm, we use a spectral norm bound on the function on the class of weight matrices, and we also use a slightly different Rademacher complexity measure. Instead of choosing a measure that's based on the norm, we add another extra Rademacher variable for every output of your layer. And the Frobenius norm to a spectral norm, this makes sense because instead of controlling the overall budget, where you could, even if you have one component, you can increase its size, we try to control the contribution of each component. And avoiding a norm-based complexity measure allows you to, and using this Rademacher complexity measure instead allows you to get separation between low rank and full rank layers. An added benefit is that this definition of Rademacher complexity satisfies a vector contraction inequality. So you can show, using these conditions, you can show that the complexity of rank R linear functions is smaller than full rank linear functions by a factor of square root R over D. So this is fairly straightforward for one layer. And now we're going to try to plug this into a chain rule, and we're going to just basically use a chain rule for Gaussian complexity from a 2016 paper of Maurer's. And this basically says allows you to decompose the Gaussian complexity of a composition of two function classes into the Gaussian complexity of one function class and a couple of other quantities. So the important quantities here are L here, which is the overall Lipschitz constant of f, D, which is the diameter of of the bottom function class, and gr hat of f, which is so the Gaussian complexity of Lipschitz coefficients of f. Now, and this is the definition of the Gaussian complexity of Lipschitz coefficients. I'm not going to go into, I'm not going to bound or get results for each of these over here, but it's not that hard. But we can, I think the key step of, or the key part of a result that allows us to get slightly better generalization bounds in some situations is by bounding the diameter of deep networks with low rank layers in a smart way. And what low rank layers allow you to do is bound the layer by the minimum rank over the chain of weight matrices rather than getting a factor that multiplies across the layers. And basically, you put together this constraint, you put together this diameter together with the low rank result for one layer and a slightly a straightforward extension to the Gaussian complexity of Lipschitz coefficients, and then you can get to our main result, which is a Gaussian complexity bound for the class of rank constrained spectral norm bounded deep networks. And when you look at this slide, I'm going to ask you to tilt your head and squint a little bit so that you don't look at this red factor here. But if we just focus on the other parts, mainly comparing it to Gulovich et al.'s result in the second row here, if you plug in and if you look at the last column, which where we compute the bound for networks with low rank layers, their complexity measure, which involves a product of Frobenius norms, will multiply the rank. You'll get an ranked raised to the depth factor, and we can avoid this by basically bounding the diameter of networks with rank constrained layers, and comparing it to a couple of other approaches from 2017 spectrally normalized margin bounds and Pack-Bayesian approach to spectrally normalized margin bounds. In some regimes, we're better. I don't want to claim that we have the tightest bounds, but I think when the depth of the network is larger than the maximum rank of the weight matrices, then our bound does a little better. But I think what this points to is that if you can, maybe you can constrain the complexity of deep networks by training deeper networks, which might allow you to get lower rank, to find lower rank weight matrices. So just to wrap up, we compute generalization bounds for neural networks with low rank layers. Our bounds are size dependent on the width, and I think there's a result somewhere in the 2018 Gulovich paper that talks about a trade-off between the width dependent factor might not be avoidable. And comparing it to other work, I think there might be a depth rank trade-off that might be worth exploring. But what I wanted to point out as the distinctiveness of our result is that I think when we're looking at generalization bounds for deep networks, we should try to go beyond biases or low complexity for one layer and then chaining that over multiple layers, and think about interactions across layers. And low rank solutions don't just imply smaller norm solutions, they also constrain the diameter of the entire deep network. So I think we should, this is one way in which you can think about interactions across layers, but I think that's one direction we should go in. So open questions. Remember the thing I asked you to ignore, which you all very kindly ignored for me for 1 second. We need to find out a way to get rid of this factor. And an analogous situation was I think back in 2015, Neshabar et al. They showed a norm-based generalization bound which had a factor that was exponential and that which was removed later. So hopefully we can find a way to get rid of that. And basically another low rank biases is only one feature of neural collapse. So can we use other features of neural collapse like the alignment across layers to also get better generalization bounds? Thanks for listening, and I'm happy to take any questions.
One a bit over, but we have time maybe one quick question.
Yeah.
Confused because you're asking us to ignore precisely what I'm a little confused because I feel like you're asking us to disregard a factor that could be precisely the problem here, since I don't know what C1 is exactly in your bound, but if C1 is comparable to, I don't know, the R in the other bound, your bound could be even worse than the other one. So maybe you can clarify what C1 is.
So C1 here comes from this chain rule. This factor in front of the Lipschitz constant.
But is it less than 1? I mean, what is?
I don't think so. It could be. So, it could be. I think it could be much larger than 1. Mauder's paper says that this could be large, and this is why it might not be that practical to use it for general cases. But I think since we're using this chain rule, our bound is going to be dependent on this constant over here. I think the larger point that like this might not be the final word on it. The larger point is that low rank layers don't just get used. They don't just reduce the norm. They also sort of constrain the diameter. And if we can find a chain rule that's with better constants, or maybe not an additive one, but something in an exponent, which is what Golovich uses to do that.
So I view your result as a conditional one.
Yeah.
If we could find C1 that could be favorable, then your bound would be better. Otherwise, that's not the case.
Otherwise, that's